All right, so objectives for this lesson. I'll just introduce what a matrix is, okay? How to find the dimensions of a matrix, and then we'll look at how we can do some addition, subtraction, and what's called scalar multiplication with our matrices, okay? All right, so there's a video here, but I'm not going to have us watch it because I'm recording here. I think that might mess things up a little bit. So basically in that video, it was just kind of introduce what is talked about here on this first slide. All right, so a matrix is just defined to be an array of numbers. The word array just means kind of like arrangement. And what you have over there to the right, you have matrix A. Notice it's represented with a capital letter. Okay? We always represent matrices with capital letters. And this matrix is made up of 6 numbers. We call each number of the matrix an element. Okay? And notice that the matrix, it has 3 columns. Excuse me. And 2 rows. 3 columns, 2 rows. Columns are vertical. Rows are horizontal. Okay? So this would be considered the first row. This would be considered the second row. You work from top to bottom. And then as far as columns are concerned, you work from left to right. So first column, second column, and third column. Okay. Sometimes it's real easy to confuse the two, like what's rows, what's columns. I know what helps me. Columns are usually like support structures, right? And they're vertical in nature. So you can think here, these columns are lining up vertically. Okay. Now, every matrix has dimensions to it, or some textbooks and Delta Math, they refer to it as the order of the matrix. So dimensions and order mean the same thing. It's simply the number of rows that the matrix has times the number of columns. Okay? And whatever those two numbers are, when you multiply them together, it tells you how many elements you have, how many numbers you have in the matrix. Okay? So for this matrix A here, I would say it has dimensions 2 by 3. There's 2 rows and 3 columns. It's a 2 by 3 matrix. Okay? Now again, matrix elements are specific numbers within the matrix, okay? So if I want to locate a specific element within the matrix, each element's represented by a lowercase letter. So if the overall matrix is capital letter A, then I would use a lowercase a to represent my different matrix elements. Okay? So notice I have A, and then in subscripts I have 1, 3. Okay? That doesn't mean 13. It means, think of it as like 1, 3. So that wants the element in matrix A that is in the first row and the third column. So if you look at matrix A, here's the first row, here's the third column. So what number are we talking about? -1. Okay. Pretty simple, yeah? Okay. So once you try practice 1 for me real quick, take a minute to fill in all those spots. All right, Kayla, what do you think dimensions for matrix A are here?
3 and 2.
So we'll say 3 by 2. Yeah, 3 by 2. That x that's there, read it as by, 3 by 2. Okay, so then the element that is in the second row, first column, what do you think?
12.
12. We agree with that? Second row, first column. Very good. All right, dimensions of matrix B. Jaden, what do you think? 2 by 2? 2 by 3. Okay. And then the element that is in the second row, third column.
1.
Very good. Second row's right here. Third column's right here. 1 is the overlap. All right, and then matrix C. Maddie, what do you got? Dimensions.
1 by 4.
1 row by 4 columns. And then the element in the first row, second column.
5.
Bingo. So obviously these are all the first row elements. And there's only one element in the second column, the 5. Very good. Okay, moving forward. So you can take two matrices and you can set them equal to one another. But in order to do that, it means they have to have the same dimensions and their corresponding elements would have to equal each other. Okay, two matrices can only be equal when they have the same dimensions, corresponding elements are equal. Okay, so in this example, I've got a 2 by 2 matrix equal to another 2 by 2 matrix. Okay, now sometimes students kind of get thrown off by this. They look at the left matrix here and they say, well, that's not 2 by 3, that's actually, or 2 by 2, that's actually 2 by 3. They think there's 3 columns. But understand that this x plus 4, that represents one whole element. And so does the 2y minus 6 down here. Okay? All right, and it's kind of the same thing over on the right side with the 2z minus 4. All right? So notice there's 3 variables to solve for here. And this is just wanting us to recognize that if the matrices are equal, then the corresponding elements are equal. So that x plus 4, that's first row, first column, it's got to be equal to first row, first column of the second matrix, which is 3. So that means x has to be negative 1, right? Okay, 2y minus 6, what would I set that equal to? 12. Add 6, divide by 2, what's y going to be? 9. And then take the 2z minus 4, set that equal to 2, right? Those are both first row, second column elements. And z is going to equal 3. Okay. All right, and sometimes students want to write those as like an ordered triple. I mean, you can, but it's not really necessary here. Okay. All right, example 3 is going to be another matrix equation. And again, at first glance, you might be like, well, those aren't equal dimensions. The left side's definitely a 2 by 1. On the right side, you might think, oh, that's 2 by 2. But again, the 3x minus 2, that all represents one element. So does the 2y plus x, okay? So I set the first row, first column element of y equal to its corresponding element of 3x minus 2 in the second matrix. Now, clearly, I can't solve that by itself because it's got 2 variables, right? So when I set the other 2 elements equal to each other, what I've created here is just a system of equations. Okay? And the nice thing is it's already perfectly set up for substitution, so I'll just plug this in right here. So 3 would equal 2 times 3x minus 2 plus x. 3 is equal to 6x minus 4 plus x. 7 equals 7x. X equals 1. And then plug that in for x in the top equation there. Y is going to equal 1 as well. Any questions on that example? Okay, so now let's perform some operations on matrices. Okay, so here I have matrix A and matrix B. What are the dimensions of matrix A? 3 by 3, right? And of matrix B? Also 3 by 3. So the first thing we want to find is matrix A added with matrix B. So the only way you would be able to add those two together is if they have the same dimensions, which they do. Okay? So if I take a 3 by 3 and I add it with a 3 by 3, I'm going to get a 3 by 3. Okay? And it's really simple. Just add the corresponding elements together. So I'm going to add 1 with 2 to give me 3. Add 3 with 4 to give me 7. Add negative 5 with 1 to give me negative 4. Then can we do the same with the rest? So you'll get a 1, a 5, negative 2, negative 6, negative 9, and 13. Okay. All right, now the next thing we're asked to find is 3 times matrix A. So this 3 is what we call a scalar. So this is an example of scalar multiplication. And it's super simple. Just wants us to take every element of matrix A and triple it, multiply it by 3. So you'll get a 3 by 3 again with elements in the first row of 3, 9, negative 15. In the second row of negative 12, 15, 0. And in the third row of 12, negative 24, and 27. Okay, and then the third example there, 3A subtracted by B. So wants me to take matrix A, multiply it by the scalar of 3, and then subtract that matrix, whatever that result is, by the elements of matrix B. Well, I set this up nicely. We already found 3 times matrix A. That was our last result. So we're going to take all of these elements and subtract them by their corresponding elements in matrix B. Okay, so 3 minus 2 would be 1. 9 minus 4 would be 5. Negative 15 minus 1 would be negative 16. Okay, then we'll get a negative 17. That doesn't look like a 17. Then a 15. Careful on this one. 0 minus negative 2, that would be positive 2. 12 minus negative 10 would be 22. Negative 24 minus negative 1 would be negative 23. 27 minus 4 would be positive 23. Just make sure on those follow order of operations. If you have multiple, you have addition, subtraction, and multiplication, just like regular real numbers follow order of operations. All right, so then this leads me to a couple properties associated with our matrix operations, okay? So for any matrices A, B, and C that have the same dimensions, okay, that's key. They have to have the same dimensions for this to be true. And for any scalar C, the following properties will hold true. Commutative property of addition works for matrices just like it does real numbers. So matrix A added with matrix B would be no different than matrix B added with matrix A. Right? And just like with real numbers, commutative property doesn't hold for matrix subtraction, right? A minus B would not be the same as B minus A. Associative property of addition, that holds true as well. A plus the quantity of B plus C would equal the quantity of A plus B added with C. So basically we're saying there, it doesn't matter what order I add my matrices in, I'll still get the same resulting matrix in the end. Okay, and then distributive property works as well for matrices and scalar multiplication. So if I have matrix A added with matrix B, and then I take that resulting matrix and I multiply it by a scalar C, that would be no different than the scalar C multiplied by matrix A first, added with the scalar of C multiplied by matrix B. Okay, so again, that's just talking about order. On the left side, you're adding first, then multiplying by the scalar, right? On the right side, you're doing the scalar multiplication first, and then you're adding. Okay. Now, I'm making a big deal about properties here right now because when we get into, there's a whole nother type of multiplication for matrices, matrix multiplication, where you multiply a matrix by a matrix. You're going to see that some of our real number properties, they don't hold true for that operation on matrices. Okay? All right. So again,